Yeah. Yeah, this is a completely optional time for you. I put out the video every Thursday at 10 a.m. except for last week because I accidentally did it on at 11 p.m. instead of at 11 a.m. instead of 10 p.m. or 10 a.m. Dang. It. Anyways, so yeah, it will always be at 10 a.m. I could move it to 11 a.m. if there was enough students to that would be able to show up for it. I'm not sure if that helps. I might even be willing to move it to noon. I can't move it any past any later than noon. So if anybody's seeing this in my class and you can find that more people could actually attend. Like right now, I have two attending, but Jada says she normally can't even make it at 10 a.m. So if 11 a.m. would help you, let me know. If or noon would help you, let me know. I'm willing to move it to either one of those. And I'm asking all of the students in this class to please email me with your preference as to whether you'd prefer it at 10 a.m., 11 a.m., or noon, and or none of the above. So if you just say none of the above, I won't count your vote as any of the times, but because you are ostensibly unable to make it to any of those times. But what I'll do is the number of people that agree to 10 a.m., I'll compare that to the number that agree to 11 a.m., and I'll compare that to the number that agree at noon, and I'll use the one that the most students can attend. Uh, if you, for instance, can attend 10, but you can't attend 11, go ahead and say cannot. So that'll help me decide some stuff too, because there might be instances where students could still attend on 11 a.m. if I moved it to then. Uh, so I don't want theirs just counting as a complete non-event. So for instance, Thean here seems to have been able to attend at 10 a.m. I wouldn't want to destroy his chance to attend at all. Uh, but if it found out that he could also show up at 11, then that would make it an easier determination for me. So, anyways, let's go ahead and get started. Anybody, and as I was saying, Jada and Thien, uh, both you're allowed to attend this or not, but as always, I will post it on the my YouTube channel. Just like I told my lectures, of course, you need to let me know if your name or your face can't be seen on the internet. If that's the case, you need to send me an email or a text message and tell me exactly what cannot be put on the internet so that I can edit the videos appropriately. I have to figure out how to do that, but so far I haven't had anybody, so thank goodness. But if I have to, then I'll do it, and I'll make sure everybody's safe and protected the way they need to be. So, any other questions before I get started on introducing the lab to you guys? You're welcome, Jada. All right, so what we're doing this week is the analyzing motion lab, and it's a lab where you're doing sort of what you did last week with the motion detector. And by the way, if you're still having problems with motion detector, I know there's some issues where some people can't download the version of motion detector. I have a copy that you can download directly from me. I've put the Macintosh version up on in week 13 in week 3 module, the lab module. You'll see it at the top of the line right after it says lab accoutrements. So if you need to download a Mac version, get it there. I had uploaded the Windows version, the latest Windows version, but for some reason it failed. I don't know if I've exceeded my I don't know if I exceeded my allotted memory for Canvas and that's why it failed, or if I just need to give it another try. So I'm going to try it again once I get you guys started. So there's one that has the letters capital M, capital A, capital C. That's the installation software for the Mac version, and there's another one that ends in .exe, and that's the version for Windows. I'm a little bit worried though because .exe means executable, and when I click on that, I don't know if the canvas is actually trying to open it, and if it is, then that would obviously cause a failure. But either way, I'm going to try to figure out some way to put it up either here or in my Google Docs or something like. Ooh, Google Docs! Just remembered that. I'll probably put it in my Google Docs. But anyways, if you don't have access to that software for analyzing motion, which is what we're doing today, the motion detector software uh, are stuff that you need. You should be able to get that from the lab. It's in the addendum. It just tells you how to analyze the photos and stuff that we sent you. So by all means, check or that we posted for you. So by all means, check that out. Does anybody have any questions on last week's lab? All right, so this week's lab is analyzing motion. I want to go ahead and start off by sharing my screen so you'll see what we're talking about. So you'll notice I have switched my modules as I suggested I was going to do. I started making the module separate from the lecture module. You can see why week three is very important because I have a ton of videos for week three because week three is normally the week that we start off covering three dimensions and projectile motion and vectors. So there's a lot of stuff about vectors in here. As luck would have it, I didn't actually get time to cover or go into chapter three this week. So I might make a video to catch us up and then let you guys watch that on your own. But either way, I'm definitely going to move all these things that are related to chapter three. I'm going to move them all to week four module since week four is when we're going to be able to start chapter three. Uh, but down here is the module for this lab. This is the actual lab report you're going to be doing. So I'll click on this and show you what it says. Okay. I'll zoom in a little bit, make it bigger. So this is analyzing motion graphs. And these are very instructive procedures. They tell you exactly what buttons to push and stuff like that in using the software. But obviously, the premise is that you have the software. The addendum is where you find a document that has links to all the downloads. So you can actually download it whether you're using a Mac version or a Windows version. You can download the software and you shouldn't have any problems with that. But every semester I have, out of a class of 24, I have, three or four students that have difficulties. So if you do, let me know. You don't technically have to be able to do it. You could, for instance, group up with someone else that actually was able to run the software, and then you can, set up a Zoom meeting yourself, and you and the person in your class that you want to make a lab partner, y'all could actually go over the video. You can ask me and I'll set up all that for you guys if you need to. I can just set up some time or several times where students can go in and do it. It could be used at this time. It could be used after lecture. It could be used right before lecture, so on and so forth. So just let me know if you need more help. But the premise is this. Last time we did motion detector, and that was a lab where we used a device that was an ultrasound device. It sent out ultrasound, which is sound that has a higher frequency than is audible, and that means its frequency has to be over 2,000 hertz. If I remember correctly, it's 2,000 hertz. 2 hertz to 2000 hertz is the audible threshold. So the ultrasound means higher than 2000 hertz. But in sending out these sound waves, they go out in a cone and bounce off an object and come back, and then the detector actually detects as well as sends the ultrasound. So when the ultrasound gets back, it recognizes it and figures out, well, how long have you been gone? And then it uses the ambient temperature to figure out what the speed of sound is in that environment, and then it computes how far away it was, so it can make a position versus time graph, or a velocity versus time graph, or an acceleration versus time graph. Actually, other graphs too, but those are the main ones we focus on, even though we very rarely do anything with acceleration versus time graphs. In this case, we're not using a motion detector to detect that. What we're doing is using videos and then analyzing the video to figure out the motion in a way very similar to the motion detector lab. In other words, we're still going to make position versus time graphs and velocity versus time graphs. And in principle, you could still take acceleration versus time graphs and even jerk versus time. Jerk is a derivative of the acceleration with respect to time, so they call it jerk. But if you wanted to, in principle, you could even do that graph. But you can do that with motion detector as well. So the big thing is when using this type of software is computers pretty much know pixels. That's all they know is they know, a certain screen or a certain window has a certain number of pixels from left to right, a certain number of pixels from top to bottom, and therefore you have, in some sense, a number of pixels per inch. Uh, but what you need for this computer to actually do physical analysis with, with the laws of physics, for instance, or at least so we could test the laws of physics, we need not pixels, but we need units of distance that are like meters or centimeters or something like that. And we also need units of time. The computer can do work with time all day long. That's not a big deal, but it doesn't understand looking at a picture. You probably had those robot tests when you're online, and they'll just have sort of a photograph, and you have to pick out the part of the photograph that's something relevant, and computers can't do that very well. So, with that in mind, you have to, one, let the computer know exactly how many pixels makes, an inch or a centimeter or a meter or a foot or whatever. And you also have to point out to the computer what the thing of interest is. And it's getting better. I mean, they've managed to use AI where they could actually detect things, but right now we're just doing it ourselves. So what you'll ultimately do is you'll open up the Logger Pro software and you'll do insert and you'll insert a movie, and a movie will pop up like this, and then you can make the window as big as you want because the bigger it is, the easier it is to analyze. And you see these are buttons like on an old VCR or DVD player or something like that, and they work the same way. But over here are some other buttons that are relevant. So remember, I told you you had to actually let the computer know, how many pixels is in a meter or a centimeter or something like that. Well, that's what this button for, set scale. So in this video, which you have a link to, it's actually in the week 3 module under lab accoutrements. It's called basketball shot. And this is one of Dr. Wright's, I want to say either son-in-law or grandson. I can't remember, but either way, it's a young guy. He went out and did this stuff for Dr. Wright. And he's just standing on the side of a basketball court. If you notice here, there is something that looks long and straight. In fact, it turns out to be a meter stick. That's what we put there, or what Dr. Wright put there for you guys to use as a scale. The important thing is when you're doing this kind of analysis with a video, you ideally want all the motion taking place perpendicular to the line of sight. So if you imagine a line coming from your eyeball, going through whatever camera you're using, and then coming out at the actual object you're studying, which in this case is going to be a basketball, or at least the plane that the basketball is in. If you take that line and find that the plane the basketball is in is perpendicular to that line, then you know that you can analyze it pretty well. You can still analyze it if it's not perpendicular, but the problem is you're getting some foreshortening. So left-right motion might also be a little bit forward-backwards motion, and therefore you're losing some component of the velocity. Up down motion could in principle be the same way, but because its axis is this way, it's fine. So you can actually do that okay. But the main thing is if you actually put in that same plane with the object that you're studying an object whose measurements and you put it parallel or in that plane so that it's literally laying parallel to the plane and perpendicular to the line of sight, then that is a good scale to use because it's the same distance away. There's no foreshortening, that sort of thing. Now, if that meter stick was, 12 meters behind him, it would be almost useless because, yeah, we could say it's a meter, but that would make the computer think that a distance this long is 1 meter when in fact that thing is quite a bit longer. It just looks like it's short because it's so far away. So once you have something that you can use to measure a real distance that you know of in the same plane, ideally in the same plane as the action that you're trying to analyze, then you can use that as a scale. So what you would do is you'd click set scale here, and then you go down and put it actually turns into crosshairs, so it's really convenient. And not only that, the middle part of the crosshairs is transparent so that you can actually see where this line and this line make a straight line, so you can sort of picture where that line is, and then the vertical one does the same thing, so you can sort of imagine where the cross is in the middle and put the end of that meter stick right on that cross and just left mouse click on it, and that sets a dot, and then you stretch it over and put a left mouse click on the other end, and up will pop a little window, and it'll ask you specifically what's that distance. I think it by default has filled in 1 meter, so you can just write 1 meter or 1.00 meters. It's not going to know the difference or care, but you say 1.00 meters, and then it knows from there on out, hey, this number of pixels, which it computes itself, is equal to 1 meter. And then it's all calibrated to meters at that point. And as I said, the time's already calibrated. But then what you have to do is you have to show the computer what is the relevant thing that we're studying, because it just sees, again, pixels. It doesn't necessarily understand the line between the white shirt and the uh, tan background is the outlines of a human, for instance. So what we're doing here is we're going to analyze the basketball shot, but we're not yet studying how a force actually causes an acceleration. So we don't want to study the part of the ball motion where it's in the person's hand. So what we do is we'll open up the video, we'll make it as big as possible across our screen for best results, and then this rightmost button will click once and it'll move ahead. There's some default setting that it has that you can change as well, but there's a default setting that says every time you click this button, it moves ahead a hundredth of a second, or eighth of a second, or 16th of a second, or something like that. Whatever it is, we can use it most of the time. Occasionally, you have to change the time period yourself, but in this case, we don't. So what you'll do is you click that, and it'll move ahead a little bit, and you'll see him getting ready to take the shot. And you click again, you'll see him still winding up again, 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 until eventually one shot will show where he's done his hand like this, and the ball is no longer touching his hand. That's the point at which you need to start measuring. So once the ball has left his hand, the very first slide where the ball has left his hand, you want to go ahead and make a mark, a point for roughly where the center of the basketball is. So you can take those crosshairs, which happen to be pretty comparable to the size of the basketball, unless you make the window really big, but you center that crosshair up in the basketball as close as you can, and it'll put a dot right in the center of the basketball, and then it'll advance forward that same amount of time, and then you do it again, and it'll advance forward, and you do it again, and it'll advance forward, and you keep doing that until just before it hits the floor. Once it hits the floor, you could, in principle, keep on doing it, and then you could study, how the ball bounces and stuff like that. But again, that's in the realm of Newton's second law, where we're taking into account forces, and we haven't learned that yet. So that's not really relevant for this lab at all. So we really just want the motion from from after it leaving his hands until just before it hits the ground, and it'll automatically make a graph as you're doing that, and it'll plot some specific variables. Like I did it this morning with my copy here on my computer at home, and it made a x position versus time, and it made a y position versus time. So the x position versus time was a linear graph diagonally up and to the right. The y uh, position as a function of time was a parabola, like you'd expect. So then you got to decide, well, what am I studying? What do I care about? Do I care about, for instance, how fast the ball is moving left to right, or do I care about how fast the ball is moving in a split second up and down? Or maybe I care about the whole velocity as a function of time, in which case I would want to analyze v sub x and v sub y, and then take the sum of the squares of those and take the square root of it to get the total velocity. There's all sorts of things you can study, but the main thing is those graphs pop up, and you can change it to other variables if you so desire. Uh, Once you're done with that, then it tells you how to do some analysis and stuff of that sort. And then there's other videos we have as well. This is exactly what the graph looked like when I did the basketball shot. You can see this green one is the y position as a function of time. This red one is the x position as a function of time. It's measured in meters on the vertical axis and seconds on the horizontal axis. And you'll notice how much better these graphs look than the ones we did with the motion detector, because the motion detector could pick up all sorts of random motion of various things in the background. This one makes much cleaner graphs. Now, then you have these tools up here, and the buttons mean different things. There's one button that does statistics. There's another button that finds a line of best fit. There's another button that finds a tangent line, all sorts of good stuff. But the procedure tells you what to do in all of those cases. Later, you'll do a little girl first riding a bike. You'll actually have her riding by, and you'll use the size of the tire from the front edge of the tread of the front tire to the back edge of the tread of the back of the front tire, and use that. Will give you the actual dimension of how tall that tire is supposed to be. You plug that in to set the scale, and then you can detect how fast she's going. You can see whether she's going speeding up or slowing down. In fact, it'll give you a dot of X position, or a series of dots for X the position along the x-axis as a function of time, and it'll look sort of crazy. It'll be dot like this and this and this and this and this. Well, if you look at the scale, what you'll find out is that the range of that highest dot and that lowest dot is on the order of, maybe a couple centimeters. So if you actually change the range of the vertical graph, where instead of it just going from I don't know, 2.0 meters to 2.5 meters. If you have it go all the way down to zero and then all the way up to like 5 meters, then those dots that are looking like all wild, they'll be a lot more horizontal and look more orderly. It's just a matter that you're focusing on sort of the wrong thing that's not that relevant. And then the instructions tell you to do a line of best fit and find the intercept on it. So it'll make a straight line like this, and where it hits the axis, that's how high that line is. And since it's a plot of, in this case, I think it might have been velocity versus time. Since it's a plot of velocity versus time, then the distance up will actually be the velocity that the girl has. That's why they did that. Another way you could do it is you could say, well, the girl's trying to go a constant speed, as you can see, because it sort of hovers back and forth between one horizontal line. But in that case, you might want to, instead of doing a line of best fit and then reading the where it intersects the y-axis, uh, if the line's not horizontal, then that's not necessarily the most relevant figure. What you might want to do is there's another button you can use, and it's called a statistics button, and it'll give you the mean of all those, the mean height of all those data points, and that will also be measured in meters per second. You'll see it in the program. So that's another thing you could use and argue that that's the true velocity as opposed to the intercept. So that's one of the things you do. Another thing you'll do is a fire truck. Another thing is like a black expedition explorer or something like that. Uh, you'll do the little girl that was riding the bike. You'll see her later. That again, that's one of Dr. Wright's granddaughters, I think. And in this case, she throws up a ball and it goes up and then comes back down. And then finally, we do a space shuttle taking off at Cape Canaveral. So you can analyze that one as well. Let me see if there's anything else I wanted to remind you about that. So you're going to analyze all those, as I said, using the software, and it'll ask you specific questions about velocity and stuff like that. And then at the end of this document, you'll see that there's something called a quiz. Now, I ask all these questions, and as always, whenever the lab manual asks you a question, which can usually be indicated by a question mark, then I told you if there's a question mark, you put your cursor in just to the right of the question mark and hit return, 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 and then scroll back up to the middle of that white space you just created, and using a font other than black, you type in the answer. But some of the questions are like this. It says, as viewed on the video, the velocity of the truck was to the, that means you have to choose right or left, and the slope of the line was, and you have to choose positive or negative. So circle correct answers. So all of the questions that are in a lab report, you're supposed to answer. So if you see a question mark, do what I told you. Put your cursor into the right of the question mark, return, return, return. Type the answer in a font other than black in that white space, and keep moving on. It's going to ask you all these questions, and then once you're finally done, they're going to expect you to have learned something about position versus time graphs and velocity versus time graphs. Therefore, they're going to ask you some questions to see how well you learned it, not unlike they did in the summary for the motion detector. So once I grade the motion detector labs that you guys turned in, I'll give you an actual key of the right answers so you can go back and make sure you got them all right. I'm not trying real hard to mark points off for you getting the wrong answers, but I want you to look at them to make sure you know the right answers, because any of these questions that I put on these labs could come up on your actual final exams or your tests in class, because I can test you on lab material as well. So I want you to know this stuff inside and out. So when you are finished with this, you do want to go ahead and seriously try to answer all these questions. And it's not cheating to work with each other. What's cheating is you just blindly writing down their answers. Okay, if you're listening to them and you're trying to make sense of it, you're trying to understand it, and then you still end up copying the answers down, you're pushing the envelope as whether you're cheating or not, but really you're not trying. I mean, if you really tried to learn from it, I don't care that you quote unquote cheated to put the right answer in. What I care about is that you keep thinking about it so that you can figure out what the right answers are and that you can later look back and be able to answer such questions. So keep on going through all this. They give you the possibilities of the various graphs for distance versus time, velocity versus time, so on and so forth. But what I was leaning towards here was, I think it's the next page. Yeah, okay. So here's where the quiz begins, and it has graphs, and they're expecting you to draw stuff on it and stuff like that. And they ask you questions. Sometimes this document doesn't print out so nice, so you can always look back at this video and make sure your graphs look like that. Because sometimes when you download them, and then open it up in Word, sometimes these graphs get all jacked up. I don't know why. I would think Microsoft Word could write their software so it wouldn't do that in going from one operating system to the other, or from one computer with the same operating system to another computer with the same, at least the same Windows operating system. It might not be the same version, but it's certainly Windows. But either way, you need to know the answers to all these questions. You need to figure them out and think them through and make sure you understand them. One thing I can tell, for instance, this A is supposed to go with this line up here, and this B is supposed to go with this line down here. And they're trying to ask you, given this graph, and notice the importance of first noticing what the graph is. This is a graph of velocity versus time. This is a graph of distance versus time. So those facts are very important, but you've got to answer these questions. And just like last week, when I told you the big important questions that I wanted to make sure you guys understood is when you're looking at a graph on a distance versus time graph, if you're looking at a graph like line C or line B or line A, what does the height of this particular point on the graph above this horizontal axis, what does that distance right there mean? What's its relevance? Okay. Also on a particular line at a particular point, because some of these could be curves as opposed to just straight lines like we're seeing here. But if you take a particular line and you find at some point on that line, let's say this point right here, if you find the slope of that graph at that point, what is the significance of that slope? More specifically, what does it mean when that slope is really high and positive or really low and positive, like close to one or close to, zero or something like that, but positive? And then what about really high positive slope compared to a really high negative slope? Or what about a really high positive slope compared to a low negative slope? So those are the two sets of questions you need to be able to answer on a distance versus time graph is what is the significance of the vertical distance between the horizontal axis and a dot on the curve? And two, what is the significance of the slope at any point on the curve? Then those exact same questions are relevant for a velocity versus time graph, but the answers are going to be quite different. So those four sets of questions are really what you should have focused on making sure you understood in the summary at the end of motion detector lab last week, and what you should also work on improving your knowledge of in this lab, and this quiz will help you do that. Okay. So I think that's pretty much it. Let me show you something else. I'm going to stop sharing my screen for a second, and I'm going to try to share my Logger Pro screen. If I can even find my Logger Pro screen. It seems to have been minimized, so I can't see that now. Let me open it back up. There we go. Now we have another one. Okay, so this is my Logger Pro screen. And this is after I just finished running the data. You can see in actuality, what I did was I first made the window really big, and then, watch, I can show you exactly what I did because we can roll it back in time. And what I did was click the button. See the button I'm clicking right here? It's this one. It goes one slide at a time when you do this. So I click, 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 click. So we're talking like 20 some clicks so far. And you see I get really far and I still haven't got the right spot. It's still sort of touching his hand there, so I didn't start there. Still sort of touching his hand there, so I didn't start there. There's where I started. And you can see all I did was I first took this, which is to set the scale. I took the cursor and I put it. Notice how the cursor has that hole in the middle? I imagine that vertical line going right through the edge of the meter stick, and then I hit the left mouse button and that made a dot. Then I came over here and I imagined that vertical line running right through the right edge of the meter stick, and I hit the left mouse button again, and then that made this green line, and a dialog box popped up, and I told it that distance was 1 meter. Then I said add a point, and I clicked right here by trying to center the crosshairs up inside the basketball. And when I clicked with the left mouse button to click that, it automatically made this run forward, and then I put another dot. You can see I sort of missed the middle there. It's probably not going to matter too much. As you can see, the data will come up pretty well. And really what it's taking is the confluence of all the data. So it expects to have a little bit of error vertically and a little bit of error horizontally. That's the experimental method. But you keep hitting add a point and it keeps advancing, and then you add another point and it keeps advancing, you add another point, and you keep doing that, and you can see that basically I stopped it right there at that point. Now I can shrink the screen again, the video screen, move that off to the side, and right here you see y as a function of time measured in meters. So you can see initially the object was a little bit more than three. What's that? One, two, three, four, five. So each one of those is zero point 0.2. So it's maybe about 3.3 meters, and it goes up, reaches some max height, which is probably on the order of 4.05 meters or something like that, and then it goes down like this. So you could use this data, for instance, to do a curve fit and find out if it obeys the y equals 1 half at squared plus v0 yt plus y0 in that case, and you can see it actually fits. You could also figure out how fast the ball is going horizontally by analyzing this x in meters. The instructions will tell you what to do, but I just wanted you to see how that's done. So let me kill this one, and let's do experiment. No data, no analyze, insert. That's what it was. So I'm going to do insert now, and at insert I go to movie, and now I'm looking for another movie that I've got saved here. It's actually in a different folder, so let me check and see if I got. There you go. It's in the Logger Pro folder. Not that one. It is not in the Logger Pro folder. My fault. It is in the It's near this one, Logger Pro for Windows. So I know that. All right. So there's the basketball shot video that I just did. Let's do. This one's the space shuttle taking off. This one's the incline uh, air track. And let's see this one right here. That doesn't seem like much. That was that. That's his daughter dropping the ball. That's the track. What's this one? That, that. Okay, let's do this one. So I open this up. Again, open up this right toolbar. Now I can click here. Again, I'm trying to line up that with the edge of the tire. Left mouse click. Why is it not doing it? I held the left mouse button down. I didn't remember doing that last time, but I held the left mouse button down this time. And we can put in 0. Let's say 35. I have no idea that that's the right answer or anything, but either way, we've given it a size now, and that really is what matters. I needed to show you how to do that. Now, what I'm going to do is I'm going to watch this whole video real quick just to see exactly what part of this tire is visible the whole journey. So it looks like I could use the center of the tire because that's visible from right here all the way to here. And that's a easily discernible point. So that's what I'm going to do. So now I'm going to add a point. I want to click the center of the tire, roughly where the axle or the hub should be. Notice it went ahead a little bit. Now I'm going to do it again and again and again and again. And you can tell I'm probably, not exactly hitting the right spot every time, but I'm trying to get as close to it as I can every time. Because we expect it to have errors. It's, the video's grainy and stuff like that, so you can't necessarily see everything. Obviously, I'm getting some up and some down. As you can see, this doesn't make a perfectly horizontal line. I think that's enough. Let me shrink this down. Let's look at our graphs. Okay. So I've got X position as a function of time as the red one, and that's what we expect. Whereas the Y looks like it's not really moving very fast or anything. So the Y height really isn't relevant at all. In this case, what we found is position versus time, but we could also change to X velocity. And now this is those dots I was telling you about. Look how they look all crazy. But that's mainly because we're looking at it zoomed in. If I change the range of the data that I displayed on the vertical axis, I could do, for instance, vertical axis, and I don't want auto scale. Maybe I'll say manual, and I'm going to go from 0 up to, let's say, 4 meters. Or four is a big enough number. I thought I chose this already. Okay. Anyways, so that's what you can do is you can change that. I don't know why it didn't work just now, but something's funny with this on my Mac anyways. So if you need any more help, let me know. But if you hover over these symbols, it normally gives you a word. So that's a curve fit. That's a linear curve fit. This is calculating the area under the curve or an integral. This is doing statistics. And this is a tangent line, and this is examine. So what they told you to do is a linear curve fit, and the way you can do that is you're supposed to just highlight the data points that you want. So I clicked the left mouse button and held the left mouse button down, and now I'm letting go of it, and I can see that this slope is a slope of negative 26.71. And notice the units are meters per second per second. So that's the slope of a velocity versus time graph. And we learned that the derivative of v with respect to t is, in fact, the acceleration. That's why it has those units. The y-intercept is what the author or the lab manual tells you to measure, and that's 7.516. Again, these numbers are completely made up because I didn't put the right tire number in, or tire size in. But the main thing is you can see there's the units. Now, 7.516 is what it got here. Let me show you what would happen if instead I did statistics. I'm using the same data points, and this time I'm using statistics instead. And it says the mean in this case is 2.078. The median is 2.069 and stuff like that. So that might even be the minimum is 2.012, the maximum is 2.43, and they are doing X velocity. So that's another claim you could make as the height of this, which is what we just did the statistics on. The height of this is a measure of the velocity. So, anyways, that's how you run the Logger Pro. Don't save any of that. I'm going back to now share this screen. This is the addendum. I'll show you that in a second on the other screen. But this is the addendum, and it says, please download the Logger Pro app as instructed below. Then you'll follow the lab as outlined. This is for the most recent version of Windows. I'm running a newer version of Mac, way newer than these. I think I'm 10 point, I think I might be even 11 about this Mac. Let me see. My operating system is Sequoia 15.1. So yeah, I'm way more farther along than that, and it's still working. As I told you, it was doing a little bit of stuff weird, but there's the link for it if you're using Windows. Here's the link for it if you're using Mac. Fairly new. If you're using some old stuff, you can use some of these, or you can contact these people. But the main thing is first contact me if you can't get it done. And then second, before you go and contact the people, you might just want to see if you can do it with an app on your phone. For instance, I have a phone app that I can use to do this, and I've got it. One of it's called Physics Suite. One of them is Video Physics. Another one is Phybox, Phyphox. That's another one that I've used to analyze videos. There's a graphing app. I don't think that one's very helpful. There is a scientific journal. That's another piece of software that I've used to make these graphs. And Video Physics is another one as well. So all of those apps are available, or ones like them are available for whatever smartphone you might have. Probably, if you have a really old phone or you don't have a quote unquote smartphone, you might not be able to find that. But that's at least two options. If you still can't find a way, then you contact me, and what I can do is at least make the video of me making the individual graphs using the videos, and then you can just take the graphs from the video and analyze it. So, any of those are possibilities. Let me stop sharing this again. And now I want to share my computer screen on my module from class. So I'm going to go ahead and put that back on the module. So now I'm going to share screen. Looks like it should be this one. Yeah. Okay. So what I just showed you was this part that says addendum right here. Okay, that was the one that had the links. This is the Word document that I showed you first. This is a video we made helping explain to you how you make the analyzing motion graphs. Basically the same thing I just explained to you, but an older version. So if you need to relook at something, you don't want to completely pull up my long video, you can come back and watch this. This one's only like 17 minutes, and you can probably get everything you need after the first 5 minutes or so. And then this is where you're going to turn it in. Remember, as always, you're going to fill in the whole Word document, turn in the whole Word document. You're going to make sure you insert graphs, data tables, sample calculations, all exactly where they're asked for, or exactly where you're expected to do them. So that means they'll either be in the procedure section, or they'll be in the section where you're doing the analysis. They will not all be at the end. If they're at the end, all at the end, they're going to lose. You're going to lose significant points because you're disobeying the requirements of the lab report. These are the videos you'll need. That's the actual software for the Mac version. I'm going to give another try to do the Windows version. You'll see it ends in, instead of DMG, it'll end in EXE. And that worries me a little bit, makes me think that might be the problem. But here's the vast ball shot video, and here's the other videos you need, as well as the space shuttle video. So that's it. I think that's all you will need to know. Do you have any questions, Thien? You can type them if you don't have a speaker that works. No questions. All right. Well, that's it. If you have any other class related questions, I can stick around for as long as you want to ask questions, to answer questions. And then today at 5:30, I have a different class. My class starts at 5:30 for Physics 242 online, but on Thursdays, I always go in at 5 p.m. So if anybody sees this, you can come at 5 p.m. today and have another chance at office hours to ask me questions. I'm trying to make sure y'all can find ways to get me. Not only that, the class is over at 6:50. So if you sign in by at least 6:45, then you'll catch me. And then at the end, after I release all the students, that's another office hour potentially. Anybody that sticks around wants to ask questions, I'll ask them. But while we're in the interval from 5:30 to 6:50, the priority has to go to the class that's happening. But after they've finished answering questions, even if it's before 6:50, then I can start answering you guys' questions. So thanks for coming. If there's nothing else, I'm going to go ahead and say bye. You too, Thean. All right. Have a good one, everybody. Bye bye. Thank you.